Hi everyone, we are back, and we've hinted, and actually we've gone over close packed directions, but we've hinted about close packed planes. So close packed planes are very important because, as we're going to be talking about later on in this class, they're going to determine essentially where most of our defects move and slip and glide and move in the planes, and they move along close packed directions within close packed planes. But how do we actually calculate if a plane is indeed close packed? So we're going to use a similar calculation to the atomic packing factor, but now we're going to use our planar density calculation. So let's look at a simple cubic structure. Let's look at the 1, 0, 0 plane, which is going to be right here. And I'm going to project that plane right here. And you know that there's going to be another plane in 2D here, 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 and I know that this is my area, or my lattice parameter A for simple cubic. So my planar density equation is just going to be number of atoms times pi r squared, the cross-sectional area of basically my circle, over area of the plane. And my magic number to be a close packed plane is 0.9069, again, geometry. So I've got a quarter, because 1, 2, 3, 4. So each of these is a quarter, so I have 1. So for my planar density there, it's going to be pi times r squared. And I'm going to divide that by my A simple cubic squared. And I'm going to see that is not a close packed plane. It's not 0.9069. So that one is not going to work. So I'm going to highlight, delete, and then what about in BCC? So if I look at a BCC structure, and I am looking at, now, the 1, 0, 0 plane in simple cubic is the closest packed plane, but it's not a close packed plane. And you notice that we can't have a close packed plane in the simple cubic because it's not a close packed structure. So the closest packed plane is 1, 0, 0, but it is not a close packed plane per se. So this is 1, 0, 0, again, projected here. Quarter, 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 quarter. One atom in the middle. This distance here is A. This distance is A root 2. Very important distinction. So I can pull this out, and I'm going to do pi r squared times square root 2, but not simple cubic, A BCC. I need 2 times pi. Still not quite there yet. So that one's not going to work either. So again, that is the closest packed plane in BCC, but it is not a close packed plane. FCC was a close packed structure, so we should in principle be able to find a close packed plane, but let's see if 111 is indeed that plane. Spoiler alert, it is. We have to get one close packed plane. All right, so I'm going to do 111, and I'm going to project it out here. So if I look at this plane, here, 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 and then here we have a little bit different type of symmetry. So we're looking at kind of a 6-fold symmetry, a hexagonal structure. I'm going to butcher this. So instead I'm going to go so something like this. So you're going to have 1, 2, 3, 4, 5, 6. So 6 at the corner. So 1, 1, 1. So a half. And then each of these are a half, as you see. So this is a half. This is basically a half, actually. So a 6, a 6, a 6. So that's a half. And then I'm going to have basically a half plus the other halves. So that's going to give me 2. And then the area. So I got 2 atoms, and the area of a equilateral triangle is square root of 3. It's Q over T. Square root of 3 over 4. Square root of 3 over 4 times that equilateral distance squared, and that equilateral distance here is going to be A root 2. A FCC times square root 2 squared. And what do you know? 0.9069, we've got ourselves a winner. We've got a close packed structure. So, or a close packed plane, excuse me. So the family of 111 planes is my close packed plane in my close packed structure of FCC. Closest packed plane is indeed 110 here and then 100 here. Closest packed, but not close packed. So I can have close packed directions, and I do have close packed directions in all the other structures, but I cannot have a close packed plane. And some materials will go through this kind of idea of polymorphism, allotropy. They can basically transfer from one structure, one solid structure to another. Probably some of the most famous carbon. So you have diamond, graphite, fluorine, graphene. Iron can be in a BCC structure or FCC structure. They usually call this austenite. They call this ferrite. Titanium exists in HCP and BCC structure. So these are all polymorphs. Lead titanate is a very famous polymorph as well. So this is a very good high-level description of basically crystalline materials. So next time we're going to quickly talk about how non-crystalline materials are a little bit more complicated. So we'll see you in the next video. Thanks. And how can we describe that, the degree of order in those systems. So we'll see you in the next video. Thanks. Bye.